Good afternoon, everybody. My name is Dr. Zoheb Borbora. I'm a learning scientist at Renaissance Learning with a background in computer science and machine learning. I'm here to present our paper titled A Theory-Driven Supervised Learning Approach for Math Skill Proficiency Prediction Using Assessment and Practice Data. This work was done in collaboration with my colleagues Dr. John Belinsky and Dr. Bruce Bray. Our apologies for not being able to attend the conference and present in person. Here is an outline of the presentation. I'll be doing a quick introduction to the problem followed by the methodology used in the paper. We'll then get into experiments and results where I'll be giving an overview of the dataset and features used in the prediction problem. We'll then go over model performance and diagnostics, which will provide some insights into the problem and the model. And then finally, we'll conclude the presentation with some key takeaways. So we investigate the problem of predicting a student's proficiency on a skill, where skill proficiency is defined as the predicted percent correct for the student who has taken at least 10 items in the skill. And it is framed as a regression problem where the target or predicted variable is the percent correct score in the skill by the student. So here are the key contributions of this paper. First, we formulate the approach as a theory-driven supervised learning problem, where we use concepts from item response theory to construct features or predictors that provide model interpretability. Second, we incorporate data from assessment and practice products to build the prediction model. Typically, most of the existing research and methodologies estimate skill proficiency or mastery by mainly looking at past performance of the student within the same skill. In our work, we incorporate estimates of student ability and skill difficulty from both assessment and practice products using an IRT-based theory-driven framework. Finally, we propose an approach that recommends the instructional category that best matches each student's current level of skill proficiency as determined by the output of the prediction model. Teachers can use these recommendations to provide appropriate level of instruction to students in the classroom. That is, these construct category recommendations can help identify whether a student needs additional support beyond the core curriculum or if they are likely to benefit from further enrichment in the skill or whether a student will be successful on the skill from core instruction only. So in this section, I'll be briefly going over some background and related work and then the methodology used in the paper. So in terms of background and related work, this work would fall under the broader theme of personalized or adaptive learning in education. In general, personalized learning has become made possible by implementing intelligent learning systems, integrating learners' preferences, analyzing individual learning data, and so on. And in this context, machine learning techniques such as Bayesian knowledge tracing and deep knowledge tracing are widely used in student modeling to estimate skill mastery by considering prior performance on items within the skill. Another relevant area for this work is that of explainable AI, which has been an area of focus in the field of AI and machine learning. And it has been gaining significance in the field of education as well. Common use cases for explanations in an educational context include educator accountability, providing individual feedback to students, giving teachers diagnostic feedback to understand where a class of students need increased focus, and in parental consultations to help them support their child's learning. In terms of methodology, we formulate a supervised learning approach where we construct features based on commonly understood concepts of student ability and skill difficulty within an IRT framework. So just to give a quick refresher, IRT or item response theory is a widely accepted methodology used in building educational and psychological tests, where students' performance on an item is mostly determined by the current estimate of the student's ability and the difficulty of the item that was presented to the student. And finally, the skill proficiency predictions from the model were converted into three instructional categories by defining two performance thresholds. Teachers can use these instructional category recommendations to provide appropriate level of instructional support to students in their classroom. In this next section, we'll be talking about the dataset and features used for training the prediction model. So we used STAR math assessment data and Freckle math practice data, both of which are Renaissance learning products. We use data from school year 24-25 for all grades, kindergarten through 12. And to filter out noisy data, we only included skill practice where the students practice at least 2 items for the skill in a day. In terms of feature set, we primarily looked at three different types of features. First were features that measure a student's ability, which could be general ability as estimated by a broad screening assessment, or it could be skill-specific ability as measured by practice activities in the skill. Second were features that are based on skill difficulty or the difference between student ability and skill difficulty. And finally, we also included features that have relevance when it comes to estimating a student's skill proficiency. These include features such as a student's grade, grade level of the skill, whether it's a focused skill for instructional purposes within the product, how much time was taken by the student to respond to items for the skill. This was meant to capture the student's engagement in responding to items. And we also included features such as the school year week, which was used as a proxy for where the student was in the school year or in their academic curriculum. So in terms of student ability features, so the general ability of the student is estimated using her most recent STAR math and STAR reading score. So STAR is an adaptive assessment which provides accurate snapshots of general math or reading ability for students from kindergarten to 12th grade. The assessment probes student ability across a wide range of skills important for grade level expectations. On the other hand, skill-specific ability is estimated using students' performance in Freckle Math skills practice. Freckle Math is a skills practice system where students practice items range aligned to a single skill in brief sessions comprising of 5 to 10 questions. Student sessions are either assigned by the classroom teacher or they're led by an adaptive algorithm. For skill difficulty based features, we look at something called as the unified skill difficulty of the skill. The unified skill difficulty or USD is based on the average rash difficulty of the items comprising the skill in the STAR math assessment item bank. This value is on the same scale as the STAR score. Next, we look at the observed difficulty of the skill, which is based on the weekly performance from all students attempting the skill during freckle practice. This is a percent correct value. And then relying on IRT, we look at the difference between the student's STAR math score and USD of the skill. And finally, we also incorporated as a feature the predicted performance for the student on the skill using a 1PL IRT model. In this next section, we'll be diving into the specifics of the model along with model performance and feature importance. So we use an XGBoost machine learning model for training our skill proficiency prediction model. And for model training, we use the entirety of school year 24-25 data, with the data being structured across a 52-week interval beginning on August 1st. Training samples were then created for each student and skill by using a 5-week sliding window. The observed percent correct performance of the student on the skill in the last week of the 5-week sliding window is treated as the predicted or dependent variable for training. Based on our exploratory data analysis, it was determined that we should consider training samples with at least 10 items practiced for the skill in the prediction week. The table here gives us a breakdown of the final dataset used for training and testing the XGBoost model. We observed that most of the students and training samples are in grades 3 through 5, which is an expected usage pattern for these K-12 math assessment and practice products. We did a 90-10 training test split on the dataset and used five-fold cross-validation for training. And then we used the grid search to find the best model hyperparameters, which are also shown here on the slide. So in terms of feature importance, we performed a SHAP analysis to look at feature importance. So SHAP or Shapley additive explanations is a game theoretic approach to explain how each individual feature contributes uniquely or additively to the final prediction output. Typically, SHAP is considered to be a more robust and accurate indicator of feature performance. And in the slide, we also see a B-swarm plot that displays the SHAP values for each feature. We observed that the most influential or predicted features include actually the observed skill difficulty from practice data, which is that skill grade percent correct mean um, uh, a feature that you see at the top. And then there are the IRT based features calculated using the difference between STAR score and USD. And then what features are also important are features that measure the student's past skill level performance across all skills and for the skills that is being predicted. So this all aligns well with what we know from IRT is that a student's performance largely depends on a student ability, skill difficulty, and ability in relation to difficulty. So next, with the table here, in this table here, we see the performance of the XGBoost regression model with the best hyperparameters on the holdout test set. We wanted to compare how the model performance on the overall data set compares to performance on specific segments, and specifically how the model does when we just have prior assessment score or prior practice data versus like when we have both assessment and practice data. We observed that the model performs best, that is, it has the highest R2 score and lowest mean absolute error for the star freckle segment, followed by the freckle only segment and then the star only segment. That's what's being shown in the table over here. This indicates that both prior practice and prior assessment scores contribute somewhat uniquely to overall model performance, and the model does better when a student has both assessment and practice data as compared to if the student only has prior assessment or only practice data. So in this next section, we'll be sharing some insights into the error diagnostics of the model. So the plots here show distribution of actual and predicted percent correct values. On the left plot, we can see that a lot of the actual percent correct scores are above 80%. That is, a lot of the students are doing well in the practice task in Freckle. We also see discrete peaks every 10 percentage points, and that is because the vast majority of skill perform practice is based on 10 items. On the right plot, we see the distribution of predicted values from the model, and we can see that a lot of the predicted values are also in this range of 80 to 100%. Um, so having understood the underlying distribution of actual and predicted values, we can then look at the error distribution of the model predictions. The plot here shows the mean absolute error with standard deviation for each predicted value from 0 to 100%. Correct. The concave shape indicates that the model accuracy is strongest in the extremes and weakest near the middle. The upper end also reflects the fact that the prediction is best in the region with the most data, which is at or above 80% correct. In this region, the MAE drops below the overall mean of 13 to 3. We see some variation in the pattern at the lower extreme, which is likely due to fewer training samples in that range and could also represent the effects of random guessing. So we believe that the low error rate in the extremes is because these predictions are for skills that are either too easy or too hard for the student, and so the model does a better job of predicting proficiency for these skills. On the other hand, we see slightly higher levels in the mid-percent correct zone, and this could be because these predictions are for skills that are in the student's region of learning. And so it is an inherently more difficult prediction task to accurately estimate proficiency in this region. So the plot here is telling us the same story by showing the mean absolute error, which is the ME, against the difference between student ability and skill difficulty, as measured by the star math score and the skill USD value, respectively. The difference is divided by 10 to help with visualizing the trend. We observe a clear relationship between USS USD difference and model performance. Model accuracy is very strong when the difference is greater than 100 and differences of over 200 are associated with MAE less than 5. This indicates that when the skill is easy for the student and the model is very accurate. These are generally situations in which students score 100% correct on the skill. Differences near zero means the student ability matches skill difficulty, and negative differences mean that the skill is harder for the student. And generally, these are associated with the actual percent correct values that is less than equal to 70%. This is likely the region of learning that we talked about in the previous slide. And the model has a harder time accurately estimating the student's proficiency in this region. At the lower extreme, where the differences are below minus 200, the skill is difficult for the student, and we can expect performance to be also saturated with random guessing. So in this next section, we describe a proposed approach that converts the skill proficiency scores into instructional category recommendations. These are real-world applications as teachers can use these instructional category recommendations to provide appropriate level of instructional support to students in their classroom. So there are three instructional categories which were established from cut points on the predicted proficiency distribution: approaching, instructional, and enrichment. The guidance provided to teachers is that students in the approaching category likely need additional support beyond the core curriculum to be successful on the skill. Students in the enrichment category would likely benefit from further enrichment in the skill, and students in the instructional category should be successful on the skill from core instruction only. The figure here illustrates the recommendation results based on two cut points of 38% and 85% on the predicted percent correct of a skill. The red dots and line represent the actual percentage of recommendations in the instructional category that were correct. So effectively, this is a measure of confidence in the instructional category recommendation based on that percent correct value. You can clearly see that the confidence in the recommendation is very high in the extremes and decreases as prediction approaches the instructional thresholds. This simply reflects the fact that model error leads to more pronounced misclassifications at or near the thresholds. With the instructional thresholds of 38% and 85% as shown here, we observe that approximately 5% of the students are placed in the approaching category, 30% are placed in the enrichment category, and around 65% of the students are placed in the instructional category. And these are students who can benefit from core instructions without additional support. So, so finally, to conclude, so in this paper, we described a machine learning supervised learning approach to math skill proficiency prediction that is highly interpretable, efficient, and can be easily expanded to include data from multiple disparate data sources. We formulated the approach as a theory-driven supervised learning problem. Specifically, we use concepts from item response theory to construct features that provide model interpretability. Results indicate that the most influential and predictive features are those that are estimates of student ability, skill difficulty, and ability difficulty difference, thus aligning well with IRT. Next, we developed a framework that uses both practice and assessment data to predict skill proficiency. Whereas most of the existing research and methodologies estimate skill mastery by mainly looking at past performance within the same skill, we incorporated estimates of student ability and skill difficulty from both practice and assessment products using a theory-driven IRT framework. This framework can be extended to include data from additional assessment practice or even instructional products to improve model accuracy while still providing a high degree of model interpretability, which is again, like you talked, is an important aspect in the field of education. Results indicate that the model performs better when there is both prior assessment and practice student data, as opposed to when there is just assessment or just practice data. And finally, we proposed an approach that recommends the instructional category that best matches each student's current level of predicted skill proficiency. The proposed approach provides confidence metrics for a recommendation and optimizes for percentage of students placed in the three categories. This approach has a real-world application as teachers can use these recommendations to provide appropriate level of instructional support to students in their classroom. And I think that was the paper. Thanks, everybody.